Hello and welcome to another video. In this video we're going to be working on replace words. And in this one you have a concept called a root which is a root of a word. So for example, if a word is helpful, the root can be help and so on. And so you have a dictionary consisting of many roots and a sentence consisting of many words separated by spaces. And you want to replace all the derivatives in the sentence with a root forming it. So you have a root and derivative. And if the derivative can be replaced by more than one root, replace it with the root that has the shortest length. Return the sentence after this replacement. So here we have the example. So these are the roots, and these are the derivatives in the sentence. So cattle needs to be replaced with cat, and then rattle needs to be replaced with rat, and batter needs to be replaced with bat. So essentially you can think of this sentence as like individual problems. So for every word, get its shortest root and replace it with a root, and then return the new sentence. So this can be said, given an array of words, return the roots of the words if there are any, and if there aren't, just return the word. And then for this one, so this goes to A, this goes to A, this goes to B, this goes to C. Now, there's a few ways to do this. There's kind of two. One that's pretty straightforward is we can use a set. So let's say we have this set of words, and let's say we're going through cattle. So let's actually make a little array. So here's our word, cattle. So like this. So we can kind of do this a few ways, and this is where you want to think about like efficient string building, efficient comparison, and so on. So obviously the worst thing you could do is you could say, okay, let's just start with a C. Is a C in our set? No, it's not. Okay, so let's add the A to the C. So now our word is CA. Is CA in the set? No, it's not. Now let's add the T to the set, or to the word. So we're literally just like adding a character. So our current word starts out with C. It's not in the set, so then we try CA, so then we try T. The problem with this is, let's say our word is never in the set and our word's like 1,000 characters. Then we're adding a character at a time, but adding a character to a string, strings are immutable in most languages. So if you have some long string, like 1,000 characters, and you add a C, you're actually basically rebuilding the entire string, and then you add a C. So that's not super efficient, so you don't really want to be doing that. So that's kind of the problem with using a set as well, is because you have to build the word every time, and also to check if a string is in a set, I think is also O of n. So to check if like cattle is in a set, you have to take all of its characters and under the hood it'll do some hash operation, and then check if it's in the set. So that's kind of the problem with the set approach, is you have to keep building the word, I think. And you have to build a new word each time, so that's pretty slow. And so is there a better way? Like, is there somehow a way we can do this like in linear time? Like, we don't have to rebuild the word every time. We can just like add one more character and reuse what we had. And so there is a way to do that, and it's using a try. And so what a try basically does is it's a data structure. It has two things. Has a Boolean value, true or false, and it symbolizes, is this a word? So maybe we could call this like is word. And it also has a dictionary, or in our case we'll use an array, but dictionary, that maps letter, so letter to another try. And you can have up to whatever letters you have. So if you have 26 total letters, like possible in your language, you can have a dictionary of length 26. If there's like 500 and whatever, you can have as many as you want. So essentially what it's going to look like, let's say we have this cat, bat, rat that we try to put into our try. So in the beginning we have a root try. So I'm just going to draw it kind of like a tree. So maybe we'll draw it like this and then move some nodes around. This is our root try. And let's just say that is a word is red, and maybe is not a word is white. Let's keep it simple like that. So our root try is never going to be a word. Well, I guess it represents the empty word. So maybe if you put in the empty word. And then the mappings are, we'll draw it in this line. So if we have an A here, that means that like this try has a mapping that is a letter A that maps to something. So let's try to put in cat. So what's going to happen here is we're going to start at the root, and we're going to go letter by letter for cat. So if our word is cat, we're going to say, okay, let's check that the C is in our try. So is this C in our try? No, it's not, because like this has an empty dictionary and it has not a word. So we're going to map C to a new try. So C will map to this try here. Now we're going to be at this try, and we're going to look for the A. Is an A in here? Is there an edge with an A? So I'm showing it as an edge, but really it's going to be in this dictionary, is there an A? No, there's not. So we'll map this to a new try again, because it doesn't exist so far, so we'll map it here. Like this. And now, in this try, is there a T? No, there's not, so let's reuse this guy. Now let's just say this maps to a new try, with the edge being T. And now that we went through this whole word cat, once we're done with the word and we're on some try, we want to mark this try as a word. So if we traverse from here and we get to here, we know that this word is in our try, and cat is in our try. So we're going to mark this. Maybe I'll just put a little check mark saying it is a word. So if a check mark, it means it's a word. So now cat is in our try. Now, let's try to put in bat. So once again, we start one letter at a time. So we say, is the B in our word? So we start here. Is there a B? Is there a path B? No, there's not. So we need a B. And also, we can keep in mind that if we ever have let's say we try to, I'll show this actually as an example later on. So we put in B. Okay, now we go to this try. Now we try to put in the A. Is there an A? No. So let's just put in an A. And then we go down to this try. Is there a T? No, there's not. So let's make a little path like this maybe. And obviously it's not a tree. Like each one of these has a dictionary, so there can be 26 edges from each one. So from here, there's a T that goes to this try here. And now we're at this try, and then once we're done with the word, we'll put a little check mark saying there's a Boolean value saying this word is true. Okay, now finally, one last one is rat. So we can draw it maybe like a different way or something. I wonder if I can move this. Let's see. Can I turn it, spin it, something? Yes. Okay, so here we're going to try to put in rat. So once again, we check for the R. There is no R, so we put in R. R goes to a new try. So there we go. And obviously this doesn't exist, so let's check this. Then the A, we don't have anything here, so we'll make another edge. And it will go to a new try with edge A. And finally a T, so we can copy this guy again. Or maybe let's do like this. And that. Okay. And this is a word now. So we have 3 words from the root, so this is our root. How do I want to symbolize a root? Maybe we'll give it a color. So here we go, root. Maybe something like this, whatever. This is our root. Actually, better idea. Let's just give it a hashtag symbolizing a root. Okay. Yeah, so now that we have this, so essentially from our root, we have 3 things. So we have bat, we have cat, and we have rat. And whenever you're in these tries, none of these are words, but whenever you get to this, this means this. If you get here, we have a word. If you get here, we have a word. If you get here, we have a word. Okay. Now let's say we try to put in, and for our example, does it make sense? Like, let's say we try to put in battle. So ideally, when we try to put in battle into our try, well, we want the shortest prefix possible, right? So does it make sense to put in battle if we already have bat? Like, will battle ever be used? Like, yeah, we can put in bat, and then we can make a further path. But really, once we traverse this try and we get to a word, we don't need anything longer. So what's going to happen here is for battle, we're going to say, okay, we start at the root. Is there a B? Okay, yes, there is. So let's go down that path. Now, is there an A? Yes, there is. Let's go down that path. Now, is there a T? Let's go down that path. And now we already have a word. So if we already have a word and we're trying to put in something longer, we don't need to. But also, let's say we try to put in, this is another thing for a try. Let's say instead of rat, we try to put in ram. So what would happen here? So what would happen here is we're going to check, do we have an R? Yes. Do we have an A? Yes. Do we have an M? No. So then we're going to make the edge of M And then that would basically give us another try. So we would say, like, here we have this, and we have another edge, and this is an M. And you can see how this can keep growing and growing and so on, essentially. So you basically either traverse if you have it or make a new edge, and once we are done with RAM, we make this a word as well. And that's kind of like what the data structure looks like. You start at the root, you always traverse the root to put in words, you just traverse down, or if you don't have it, you create a new one, and then once you're done with the word, then you just put a little Boolean value in. So now, how is this going to be useful for our example, our cattle? Well, it's going to be a lot better because we can just take our word, we can start at the root, and we could say, okay, let's just keep traversing. If we ever hit a word, we'll just return that word. And if we never hit a word, we'll just return this whole thing. So what's that going to look like? Well, do we have a C? We can just traverse character by character. So do we have a C? Yes, we do. Okay, we have that. Now, do we have an A? Yes, we do. Okay. Do we have a T? Yes, we do. And it is indeed the end of a word. So, because we're at the end of a word here, we can just return the entire word up until this. So we can just return cat. And now notice we didn't have to like keep building the word. All we care about is the current character we're on. We just check, is it in our try? So to put in a word into a try is O of n, and to traverse character by character is O of n, instead of rebuilding the try or rebuilding the string every time and doing set comparisons. So it's cheaper. And let's say instead of trying to look for cattle, we try to look for cabble. So what's going to happen here is we can just say, okay, well, we were here. If ever our letter is not in our try, so in this case, we have a B. We don't have a B in a node here. We don't have like a path. So from this B, you can't go anywhere. So we're guaranteed that if B is not in here, obviously this whole thing isn't going to be in here because we don't have a path. So if we don't have a path, we can just return the entire word because this word, none of this is in the try. So that's the other thing that's useful about the try is once your current letter is not in your try, then the rest of it won't be either. So as soon as it's not in the path, you're just done. And so now we can just easily go through this for every word, check if it's in the try, letter by letter. If we ever get to a check mark, then we can just return that prefix. Otherwise, we'll just return the whole word if we never got to a check mark or it's not in the try, right? Because like, let's say we store cabble, obviously not a word, in our try, but then we're looking for cab. Then what's going to happen here, or to make it simple, let's say we have this original try, but instead of these words, we're looking for C. So if we're looking for just the character C, like this is our string, just C, get rid of all this guy. Well, we'll say like, okay, well, C is in here, but it's not the end of a word. So it's kind of like whichever one you get to first. If you get to the end of a word here, then you return the word. And if you get to a word here, then you return that prefix. And if whatever you're traversing is not in your try, then you just return the whole word. So let's take a look at the code for all that. So here we have, and I didn't want to code this in person because it's a lot. So for a try, some basic stuff that you can have that's useful. So like I said, you have a Boolean value is word. And you can either have an array or a hash map called children. So in our case, we have an array. So instead of these being keys, we can just have an array of 26 values, and 0 will represent A, 1 will represent B, and so on and so on. So in Java, I said you want to stick to arrays, and I've shown how to convert from like a character to an index and so on. So here we have insert, and this is how you insert. So you start at the root, and then you go through the whole word, and you get the index of where you need to be going, right? So the index is basically the letter converted to an index. So you just take the current character, subtract A. I talked about how this works already. So this is basically just, if A has an ASCII value of like 97, which I think it does, and we're on character D, D will be 97 plus 4. So essentially you're doing 97 or 97 plus 3. So it'll be like 97 plus 3 minus 97, which will give you index 3 and so on. So you convert from a character to an index where A is 0, B is 1, whatever. And if this edge doesn't exist, we create a new edge by making a new try in our array. So essentially it's an array of character to try, just like the dictionary, right? you have a try, and then you have a dictionary of key to try. Same thing with an array. You have an array of index to try. So if it's not there, you make a new one. Then you just traverse to the next try, and you check if the current try is a word. We don't need to put in a bigger word because that will always be used. So if it's already a word, we can be done. And once we're done traversing the entire word, then whatever try we're in becomes a word. So you just set that Boolean value true. So there's some common functions in a try that you want to use, like this is pretty standard, and then insert, and you can try like remove, think how remove would work and things like that. And there are like LeetCode problems for this, but it's a pretty rare data structure, but kind of useful. As you can see here, it's super handy. So here in our actual function now, we just make a try. For every single word, we insert it into the try, and then we have our result, which can be a string builder. We split our word. You can technically save some space by not splitting the word on the empty space. You can use indices to use like the start and end of a word. So you can have like an index of like the start of the word, an index of where you're at, but it makes the code kind of a mess. So I just did it this way. It makes it a lot easier. And then basically, if we have more than one word, we're going to put a space between the words. And then we have this function find root, and the find root will take the word and determine is there a prefix or do we want to return the word. Then we just take that whole builder return string. So let's take a look at this function. This is like the core of the logic. So for a try, you always start at the root because you're seeing like I'm looking for a word and I need to start at the root. So you start at the root, then you get the prefix. Then for every character in the word, you check the index you need to be traversing. So if this index doesn't exist, or if this index does exist, then we want to be adding the character, right? So basically, like, does this path exist? If the path does exist, then we want to add the character to our result. We technically don't need to do that, but I guess this is fine because we have a string builder, so I guess it's fine. Like, you can either add to the result as you're going, or you can just like return the thing. It doesn't really matter. Like, you can just keep track of the indices. It doesn't really matter. But essentially, so if there's a path, we're going to keep adding this to the prefix, and then we're going to traverse the try. And if this current prefix is a word, we return it. Otherwise, we break out. And if we ever break out, we can just return the word. I guess the reason why you would want to add to the prefix is because it uses like word to car array, which you can also use like index values as well. Personal preference there. But basically what you're doing is you're just going through your word, you're traversing your try, and then you hit one of three cases, I guess. Either your word is not in your try, which means you would just break out of here, right? You'd basically hit this condition, or it would be the else case. You'd break and return the word. Or your word is found, which is this case, which you just return the prefix. Or you keep traversing, but then you never actually hit like the end of the word, in which case you would just return the word as well. So because the prefix would be the word, so either one. Basically you do that, then you just return the result. So this is a good problem to use tries, and you can figure out like why is a try better than a set, like I showed earlier, because you don't constantly have to it's very efficient string comparison, because you're just comparing one letter at a time, as opposed to like checking, as opposed to keep building the string and keep checking a set. Now another thing you can do, I guess, is string hashing. So you could look into that as well. And the basic idea for a string hash is you can convert a string into a unique number, and then you can check, is that number in my set? Which is more efficient because then you can just take your number that you had before, add that one character, and then keep going. I think the number might change though. Like you might have to do more than that. I'm not sure. Maybe you can do string hashing, but string hashing is a lot harder than a try, and it's usually for like hard problems. I think I did a bunch of problems on string hashing if you wanted to look into that. But essentially, this is like the solution that's preferred, I think. Definitely set is like the worst. So, and this is pretty good. And so let's talk about the runtime and all that stuff. Okay. So essentially, time. So to insert a word into a try is O of W, where W is the length of the word. So we're already doing that. So let's say D is like the length of the dictionary, and W is the length of each word. So it would be something like this to insert into the try. Then for the sentence, let's say S is like the length of, or the number of words in the sentence maybe, and then W is the, or whatever, is the length of each word. So essentially you basically have to do that again. So you have to go through every single word. You have to, so you're splitting the sentence, which is O of N, and then you are going through every single word and you're seeing, is it in my prefix? And like I said, though, the nice thing is for the word, it's actually going to be linear time to split the word and to like go letter by letter. You're not like rebuilding the string. Like I guess technically you're using a string builder here, but I don't think you can compare like a string builder to a string. So a string builder is, from what I know, basically like an array, and then to compare it to a string or to check if it's in a set or something, you still have to call this toString function, which basically makes your string builder like an array of characters, and then you convert it to a string. But anyway, we don't need any of that. So I think it's going to be something like this for time and space. So like I said, you have to store every single word in the dictionary in the try. So that's going to be worst case D times W, because imagine all your words are different. And then we also did split our sentence, and we're storing that. So that's going to be the same thing. You can get rid of this if you want to, but then it's going to make the code a lot messier, because then you have to have two indices. Generally, you can do that as well. But yeah, that's going to be all for this one. Hopefully this was a useful introduction to tries. You can try some try problems. There's a decent amount. And if you have any questions, as always, please write in the comments, and I'm happy to answer them. So thanks for watching.